math class. In this class, we want to consider this topic in mathematics, which is circle geometry. And first thing you need to understand the word circle. So what's a circle? You can define a circle as a locus of a point. So let's say locus of a point, locus of points, equidistance from one piece from a fixed point, equidistant from a fixed point. So here, let's say this here we have a fixed point, and we can label this fixed point as point O. Then the locus of a point equidistance, it means with equal distance. We can indicate the distance. The distance might be given maybe 4 centimeter or 3 centimeter. So with this distance here, this point moving with equal distance from this fixed point. So this is what is called a circle. So that's the locus of a point, equidistant from a fixed point. And this fixed point is the center of the circle. And this distance here is same thing as the radius. So that's the definition of a circle. And next, also, we need to have some parts of a circle. Like we have the radius. So we should be able to identify the radius. We should be able to identify diameter. We should be able to identify what is chord. These are important parts of a circle that we need to understand and recognize. Also, we need to understand what an arc is. And we also need to understand what a sector is. Also, what a segment is. Now, let's look at this in a circle. Let's have this circle here with center O. Then, the radius is a line that is drawn from the center to any part of this circumference. So, a line drawn from the center to a part of the circumference, we can draw it in any direction. So, if it is on this direction, so this from the center to the circumference. So this line is what is called a radius. And a diameter is a line that is drawn. It passes through the center and touches the circumference at two other sides. So touching the circumference at two sides and pass through the center. That is, if we draw this line, extend it to the other side here. So this line from here to here is also a radius, which now make it to be a diameter. That is, diameter now is same thing as 2 radius. 2 radius give us diameter. Okay, so if you like, we can draw it another way, or we can write it on top here as this line is a diameter. So a line that draw pass through the center and touch the circumference on two sides is a diameter, and which implies that 2 radius now, or 2 radii now, give us what is called a diameter. Then next, we need to understand a chord. A chord is a line which is the circumference at two sides. Now, let's draw this line here. This line touches the circumference on two sides here, on this side and on this side. Now, this line is called a chord. So that's a chord. It can be at any part of the circle. So we can have it this way. It's also a chord. So it doesn't matter where it is drawn. So once it is a line that touches the circumference at two sides, that's a chord. Now this distance around the circle is what is called the circumference of the circle. So that is that. And also we need to understand that a diameter is also a chord, but is the longest chord of this circle. So diameter is also a chord, but the longest chord. Now that is that. Now what is an arc? An arc is just a part of the circumference. Don't forget that distance around the circle is the circumference. So an arc is just a part of that circumference. So if we cut any part of the circumference, let's say from here to here. So this length here, from here to here, is just an arc. So we have arc here, and which is going to be the smaller one here. So if from here to here is an arc, it is, small compared to the other one. So we call this one the minor arc, while this one will be major arc. So that is that. And also we have a sector. A sector is a region that is surrounded, or we can say a region bounded by two radii and an arc. Two radii and an arc. So now considering this arc, let's take this radius here. Let's take another radius from here. The center to the circumference, that's the radius. So this is R, this is R. So this is two radii, and from here to here is an arc. So this region here bounded by these two radii and this arc here. So this region here is what is referred to as sector. So inside there we have what is called sector. That is a region surrounded by two radii and an arc. And also, what is a segment? A segment is also a region surrounded by a chord and an arc. So we have a chord. Let's consider this chord now. And this arc from here to here is also an arc. All right. So this region bounded by this chord and this arc is what is called a segment. So this region here is therefore a segment. Or we can use another something. So here we call this area segment. So it can be formed in any way. So it depends on how the chord is drawn. And also here, there is what is called a minor and a major. For the sector now, this one shaded here, bounded by this radii and this small arc, is a minor sector. That is smaller. And the other one that is not shaded, bounded by this major arc and these two radii, is also a sector, but is a major sector. Okay. And similarly for segment, we have what is called a minor segment. So this region that is shaded here is smaller, so it's a minor segment because it is bounded by this chord and this minor arc here. Why the other side, that is this chord and this major arc that is not shaded, is now the major segment. So these are the parts of the circle that we need to be able to identify, that will help us when we are working on circle geometry. So now we want to look at some lemma. Let's call it lemma. That is what we need to know before we enter the theorem. So we call it lemma here. Now the first one is that a chord can subtend angle at the center of a circle and also at the circumference of a circle. Now for the first one, a chord or an arc subtend two angles at the center of a circle. So let's consider it. What is the meaning of subtend? So we need to understand this word subtend. When another word for subtend here might be formed. When something is formed by, when an angle is formed by a chord or an arc. So, and this is telling us that a chord or an arc can form two angles at the center of the circle. Now, consider this circle here with center O. Now, we are going to draw a chord. So, it might be a chord or an arc. So, let's have this as a chord. And let's call this AB. Okay. So, it means that this chord here, AB, so if it is not a chord, it means we are not going to draw this line. We are just going to mark an arc, all right? Now, this chord AB here can form an angle at the center, but two angles, right? So, it means we join A to O here, and also we join B to O here. So now, it makes this chord now to form this angle at the center here. The one inside here, that's the interior angle, which is somehow called obtuse angle. An angle that is less than 180 degrees or greater than 90 degrees, right? Now, and this other one outside there, which is the exterior angle, that is a reflex angle, the angle that's greater than 180 degrees or less than 360 degrees. Now, to understand here that we have two angles at the center here formed by this chord. So the one inside and the one outside, that's the first thing. And number two, also we need to understand that also a chord or an arc as well, an arc subtend angle can subtend angle also two ways angles at the circumference of a circle. And let's see that as well. Let's see to that as well. So we are going to draw the circle now, and of course we can see indicate as the center here. And let's look at something. When we have the chord like this, okay, let's have the chord this way. Now, this chord has shared this circle into two parts, two segments, the major and the minor. Now, this chord here can subtend angle at the circumference of the circle. That is, the angle coming from here, forming at the circumference, and also be here, joined together. It means that this chord formed, that is subtend angle at the circumference. So we have this angle, we can call it C here. So we have angle ACB at the circumference. So we can label this as, here we have angle AOB, obtuse, the first one, and also we have angle AOB, which is reflex here. Okay, now the same way we can label this here as angle ACB at the other side here, and also here it's formed on this side as well. So when we label this as D, also we have angle ADB, ADB at this other side. So that's how a chord or an arc can form an angle. Now, if this chord is not drawn, we look at it as an arc. So the same way, if the chord is not drawn, we look at this as an arc. So that is that. And also, we need to understand that a chord, which is a diameter, A diameter can also subtend an angle at the circumference. Let's consider this. So if we have this circle at center O here, you know, a diameter pass through the center of a circle. The line that passes through the center of a circle here is what is called a diameter. So this diameter here form an angle at circumference. That is, we have this angle here because it's also a chord. We understood that a diameter is also a chord, but the longest chord of a circle, right? So, but here, this angle here will now be 90 degrees. Is a theorem on its own. When we get there, we'll be able to see why it is angle 90 degrees. So, angle formed by a diameter, the circumference is 90 degrees. Okay. Now that we have this lemma here, let's move to theorem 1 now. Let's look at theorem 1. So we call this theorem 1 in this class. And this theorem states that the angle subtended by a chord or an arc at the center of a circle is twice that which the chord or arc subtended at the circumference of the circle. So we are going to look at this theorem. How is it like this? Or why is it twice? Now let's look at the theorem. It says the angle subtended by a chord or an arc at the center, right? We have been able to see how a chord can subtend angle at the center, right? Now is twice. That's the key word. Those are the key words there. So angle at the center is twice that which the chord or arc subtend at the circumference of the circle. Now, whenever we are proving any theorem, we need to state out those things that are given. Now, we are going to be stating them out from here. Those things that were given from the question. That is, we can see that given a circle, we can list it out. A circle, center O. So we have a circle center O, and of course, we can demonstrate this by drawing it in the diagram. And we have this as a circle. Okay, we can try and make it a little bit bigger than this, right? So we have a circle with center hole like this. Now, what else are we given from this question? From this theorem? This is center hole here. Now, let's consider this. They said the angle subtended by a chord or an arc. So, we expect to have a chord. A chord. Let's use chord here. It might be a chord or an arc. A chord AB. You can label it as AB. So when you draw the chord here, and you label this as A, this as what? B. Then we have an angle at the center. So we can write this out, and we say angle AOB at center. So that means we are going to form an angle from A join to O, also join to B. So that makes this to have angle at center. And don't forget that we can form two angles here, the obtuse and the reflex. All right. But now we are going to consider the obtuse for this, proof in this class. So we can say angle AOB. We can say obtuse angle AOB at. Now, what else are we given here? Also, now the student say is twice. That way they called or have obtained it as the circumference. Also, we have an angle at circumference, okay, which implies that we can say we have angle ACB at the circumference of the circle. Now we are going to form an angle as well here with this at the circumference. We can form it on this side here. So joining points A to B. So this angle is at the circumference, while this angle is the obtuse angle that is center. Okay. So we label this as C now because we say ACB. Now we want to look at some things here. Now, before we go to the proof now, what does it require for us to prove? So we need to write out required. Required. What are we proving? So we need to state it. To prove that angle AOB, that's angle at center, is twice. Is in mathematics is equals to is twice. That's twice means two times angle at circumference, that's angle ACB. So this is what is required of us to prove in this class, in this particular theorem. Now, we now want to do something next, which is called construction. We are going to construct construction. So we have to draw join line CO, or let's call it CO. Join line CO. This is C. Join CO with a line and extend to external point and extend to point D. Let's call it D. So now we can join this line now. Join this point with a line from here and extend to, let's say, point D here. So that's the construction we have drawn here. Okay. Now let's now look at the proof now. So the proof, we are going to be stating some facts on this diagram. And some facts here remains that when we consider this line we construct now has divided this, into two triangles. So we have, you can say from triangle AOC. So this is triangle AOC. Now let's look at it. Triangle AOC. Now line AO is equals to this line AO is equals to line CO. And why are they equal? Because they are radii of same circle. This is what I'm saying. This line is a radius. This line is also a radius. That's what make them equal. Why are they radius? They are both coming from center of the circle. This is drawn from center of the circle to the circumference, also from center of the circle to the circumference. So that makes this AO to be equal to CO. And that therefore AOC now has two sides equal. Don't forget, whenever we have two sides equal in the triangle, that triangle is known as isosceles. So hence here we say hence triangle AOC is an isosceles triangle. And one of the property of an isosceles triangle is that the base angle as well will be equal. So this angle and this angle are the base angle now, which are going to be equal. So we can call it x here, x here. So that is, we can say that therefore this angle I want to label it now using the three letter angle CAO is equals to angle, also we label this as angle ACO, and we can call it letter X. So that's what we have done here. Okay, now also that's why we need to know some elementary theorem as well. The exterior angle of any triangle is equals to the opposite interior angle. Now this angle here is the exterior angle from here of this triangle AOC. So you can see that the one side is extended. So this is the exterior angle, and this exterior angle is equal to the sum of these two opposite interior angle. So we can call this as 2x here. Alright. So this angle is 2x, and we can state it as angle AOD, because this is angle AOD. AOD is equals to 2x. That's exterior angle of triangle AOC. Alright. Now we are done with this part. We can do the same thing for this part. So similarly now we can say similarly triangle AOB, this other side, sorry, it is triangle BOC. Triangle BOC is also an isosceles triangle as well. Why? Because we have line BO is equals to line CO. Both are radar of same circle. So the same thing we have BO a radius, CO a radius, making these two sides to be equal here, and therefore the base angle also will be equal. That's the property of an isosceles triangle. And since they are equal, we use same letter. This is y, so this is y. So now let's now look at something here. In the same way, this triangle here, one side is extended as well. That is, we have this as the exterior angle. That means exterior angle is equal to the sum of the two opposite interior angle, and this is called 2y. So we also state it here that angle BOD, also angle BOD is equals to 2y. That's exterior angle of triangle BOC, right? Now we want to make a conclusion here. Now remember that we are after the angle at the center AOB and angle at circumference ACB. Now we want to write angle at the center now AOB. Look at it. This angle AOB, all this angle here, 2x plus 2y. So I can say angle AOB is equals to 2x plus 2y. And what happened here? 2 is common. We can factor it out and we have 2 into brackets x plus y, right? Now, looking at the circumference here, which is angle AB, all this angle here, we can also say that angle ACB at the circumference is equals to x plus y. Are we there? That's okay. That's because this is x, this is y. So everything here will be x plus y. Then what's happened now? Well, we can see that we have x plus y here. So instead of writing this x plus y, we can as well write angle ACB. So that means I can now say angle AOB is now equals to 2 times, because bracket means times, that's 2 times angle ACB. So that's the proof. That's the proof of theorem. So we have proved this. Why? Because the require has been shown. So that is that. So that's the proof of this theorem. And this theorem is like the reference point to all other theorems. So if we're familiar with this theorem very well and we can prove it, and we recognize some certain things like the two sides that are equal, all those things. So it will be easier for us to solve problems on that circle and also prove some other theorems as well. So if you are watching us for the first time here in Master Teamers Lab, why not give your thumbs up and share this video, also subscribe. Now let's consider an application of this theorem before we look at theorem 2. It's very direct application to this. Okay. So as an example now, look at it as an example. We have given this circle, sorry, let's draw it. Let's redraw this. So we have example to the theorem 1 now. So given this circle here with center hole, and here in this case we don't have a chord, just an arc. So and they call this as A, this as A, this as B, just like arc AB now, which form an angle at the center. And this angle at the center is given as 130 degrees. And they now form an angle at the circumference with these 2 points AB, right? And they call this point as point C. And in the question, they've already done something like this. They've joined C to O and they extend it to another point, say D, something like that. And they put an angle here as 26 degrees. And the question now says we should find, first thing they want us to find, they say 1, find angle, value of angle CBO. You know, when you have 3 letters like this, it means that the line angle between the line CB and line BO. So B is the reference point there, CB and BO. So CB and BO. So this angle here to find it. And the second one as well, they say find angle BOC. So that's between line BO and line OC. So BO, OC, also this angle here. So we want to find these two angles. Now, looking at this now, we see that once we know theorem 1, easily we can, solve this particular question. Now, theorem 1 states that angle at the center is twice the angle at circumference. In other words, it means that once we know the angle at the center, we can know the angle at circumference and vice versa, right? So it means angle at the center will be double that of the circumference. So now angle at circumference is ACB. So I can say angle ACB is now going to be half of 130. That's 130 divided by 2, right? Because why? We have angle at center equals to 2 times angle at circumference. So that's just the reason why. So in the same way, if it is circumference, we can multiply by 2 to get the center. So that's the application of the first theorem. That's the application. So what I'm saying in essence is when we have something like this and we have this, form here and this, angle at circumference, if it is, let's say 30 for instance, your angle at center will also be 60 degrees. Why? 30 times 2. That's like, and if it is this one, you divide by 2 and you get it. So angle at center is twice the angle at the circumference. Now, which implies here, this become 65 degrees, right? Now, something interesting is here. Let's look at it. It means that all this angle here will be 65. right? So let's take note of that. Well, now we can see that this is 26 degree here. This angle is 26 degree. And when you consider this, you can say triangle AOC. Look at the triangle AOC will be an isosceles triangle, is an isosceles triangle. Why is it an isosceles triangle? Now, we established that AO is equals to CO. Why are they equal? You must know all these things. And why? Because they are radii of same circle. They are radii. Look at it. AO, CO. They are both radial. Why? From the center to the circumference, there's a radius. From the center to the circumference as well is a radius. So, which make this triangle AOC to be an isosceles triangle, and therefore the angle here and the angle here are base angle, which are going to be equal. So I can say this angle as well will be 26 degrees. So we can write it out and say angle ACO is also equals to 26 degrees. Why? Base angle of isosceles triangle AOC. So it's very important for us to state it out like that. So that's how to solve riders in circle geometry. And something will come to our mind here. Something will come to our mind. Remember that everything here at the circumference, we got to be 65 degrees, right? Now we can get the remaining parts here. We just need to say 65 minus 26. And this angle I mark here is angle BCO. So I can say angle BCO will be to 65 degree minus 26 degree, which is going to be 39 degrees, right? So this angle here now is 39 degrees. And we are finding this angle. Look at it. Also, triangle BOC here is also an isosceles triangle. Why is it an isosceles triangle as well? Because BO and CO are equal. And we expect this angle and this angle to be equal. Why? This angle and isosceles triangle are equal. So this angle is also 39 degrees. So we cannot say, therefore, angle CBO is also equals to 39 degrees. Why? This angle of isosceles triangle BOC. Then, also now, we are finding angle BOC now, this angle here. And we know that since this is a triangle, two angles are known. The third angle can be known. Why? Because angle in a triangle sum up to 180 degrees. So, which implies here, the first one here, the second one now, which is angle BOC now, will now be equals to 180 degrees minus these two angles here. And when we sum it, that's 78 degrees. So we can say that's angles in a triangle. That is, this now equals to 102 degrees. So that is one of the application of the first theorem. So I believe we are understanding this. So to show us your support and put your comments, also share this video and also subscribe so as to be aware of our videos. In this channel, we upload videos daily in mathematics, which you might find interesting. So stay tuned and be part of us. Now, let's consider theorem number 2. We call this theorem number 2 in this class. So we call it theorem 2. And this theorem states that the angles, all the angles subtended all the angles subtended by a chord or an arc in the same segments of a circle are equal. So all the angles subtended by a chord on an arc in the same segment of a circle are equal. Now let's look at this diagram. So because here we just look at the proof of this theorem briefly. So it follows from theorem 1. So let's say this center O of the circle. We have O as the center, and of course we might be looking at a chord or an arc. So whichever one, let's consider this as AB. So if it is an arc, this arc AB. But if it is a chord, we can join it and we have this line as a chord. Okay. Now, you know this chord now has divided this circle into two segments. You have the minor segment and the major segment. And what this theorem is saying is that all the angle forms, it means that it might be more than one angles. It might be 2, 3, 4, 5, as many angles. So all the angle form by this chord now in one segment. So let's take major segment now of a circle are equal. Now we are going to be forming it one after the other. We form the first angle here. Let's say the first angle here is formed this way by this chord. We have this angle here. Okay. By this same chord now, we can form another angle here. Also in the same segment, right? And we can also form another angle this way. Also in the same segment. If you like, we can form another one by this chord, also in the same segment. Now, what the theorem is saying is that all this angle, if you like, you can label it as C, D, E, F. So all this angle here, the theorem says they are equal. They are equal. So that is it. And the theorem follows from the first theorem. And when we draw a construction line here from O, we can join it point A here and also join O to point B. And what happened here? You discover something here that this also form angle at the center. Now we have angle at the center and we have angle at circumference. Don't forget theorem 1. If this is x, this will be 2x. Why? Angle at the center is twice angle at circumference. Now looking at this now, this is also at the circumference. So what makes this one to be 2x? It is double of this one. That's twice that of circumference. So this also should be x. Also this is circumference as well. And this at the center. 2x here. Also x should be here. So 2x here. Also x should be here. So which implies that this is also the angle at circumference. This is also angle at circumference. This is also angle at circumference. This is also angle at circumference. Corresponding to this angle at the center. So that is theorem 2. So easily, whenever we see any problems that looks like it, we'll be able to recognize, even if there is no chord. For instance, you see something like this, you might see that these two angles here will be in the same segment here. So whatever this angle is, if this angle is 50 degrees, so this angle also, if it is x, it means x also will be 50 degrees. And for instance, if they say this angle is 70 degrees, and they say this is y, also y now will be equal to 70 degrees. That's angle in the same segment here, also in the same segment here. So that is how it works in circle theorem. So this theorem as well is very important, And one beauty in circle geometry is that we can combine as much as 2, 3, 4, 5 theorems together in one question. So the one we can see first and we can handle first, we start writing it out and we lay on it until you're able to solve it completely. So that is that. So let's stop here like this in this class. So we stop at theorem 2. By the time we meet next class, we consider some other theorems. So why not stay tuned and subscribe? And thank you for watching. See you next class and bye for now.